Hello guys, I'm Venkatachalam, and today I'm going to explain you decision trees. Please, if you are uncomfortable with something, if you didn't understand something, let me know, and I will gently respond you in the language you want. Well, Spanish and English, because that's the only one. That's the only that I speak. So today we're going to learn decision trees. What are my objectives? Firstly, I want you to motivate you first. And thirdly, we're going to identify real-world applications of decision trees. Then we're going to understand what are decision trees and what are they used for in the industry and whatever applications you want. Then we're going to understand how decision trees learn. So notice that first we're going to see why, then we're going to see what, and then we're going to see how. And finally, after watching the theory and study it, we're going to make a more practical exercise, and I'm going to show you some pseudocode for implementing it. So this is the outline what we're going to follow. And before continuing, I want to remember something, is a change of paradigm, because we are quite used to the traditional programming paradigm in which we, as programmers, we define explicit rules that we have inputs and we pass inputs to those rules that are expressed in the form of a programming language, and we obtain answers. However, there are quite a lot of problems that cannot be easily solved with this paradigm, because there are problems quite complicated. For example, if you want to classify an image, well, how would you do that with explicit rules expressed in a programming language? It's quite difficult. So the change of paradigm is that in machine learning is that we've got lots of data. We've got huge amounts of data, and we use that data that already has the answers to learn the rules that allows us to map from the data to the answers. So before going any further, I want you to talk to me about what did you read in the machine learning introduction book. That's the change of paradigm that this diagram represents, and it's quite useful, because as I said, there exists lots and lots of data that we can learn from. And these rules, notice that we can go from here to here, because if we've got rules, then we've got more data, data for which we don't have the answers. And we can use these rules that we learned with the data that does have the answers. So we apply it and we get normal answers. So this allows us to solve lots of problems. And that's why it is interesting for us. So what are they used for? In healthcare and in medicine, maybe you will use decision trees, and physicians also use decision trees to predict the risk of a heart attack. For example, imagine that you've got lots of records of people that have suffered from a heart attack in the last 5 years, and you want to predict, and you have features about them, like what is their weight, their age, or something like that, their sex. So there's lots of features that we can map those features to a prediction. So we can get the rules that allows us to predict whether a person will have a heart attack in the next 5 years. That's a quite exciting application of this. Another one is finance. What happens if you, for example, I've seen this, and I know people that is working on this, on fintechs that automate the process of approving loans. Approval loans. And you, as a customer, you want to know why your loan was approved or not. And that's an advantage of decision trees, because they are quite interpretable. And that's why we are learning them. So decision trees, why we will use them? Because they are quite simple, they provide meaningful insights about the data, and they can be extremely powerful. As well, they can learn nonlinear decision boundaries. And this decision boundary we're going to see next. It's quite important. Again, if you've got a question, don't doubt and ask me. You can interrupt me whenever you want. You can do it in English and Spanish. I don't have any problem. Chat. Into the chat. Yes. So, what are classification decision trees? Remember, today we're going to be focusing on classification decision trees with categorical data. That's exactly the instructions that you've got to implement the final project or the capstone project. So informally, a decision tree can be seen as a collection of nested if statements that output a discrete value. That discrete value is the class or category or label predicted. When I say this, I mean that these or these or this could be used within any distinction. And you will, if you read the literature, you will find authors that use the word class, the word category, or the word label to refer to the same thing. So that's why I'm doing this. And we want to predict this discrete value given a ordered tuple of discrete values. This ordered tuple of discrete values is nothing more than the categorical data that we're using to predict. Later, we're going to see an example of this. So maybe you've seen this meme. They say that artificial intelligence is nothing more than a collection of nested if statements, but this is just the tip of the iceberg. Why? Because this is just the result of doing what we are going to do today. And I'm going to make a little spoiler, and that is that we're going to learn how to program a program whose output is a program that classifies data. So I hope that this claim be motivating for you. So, and this is the point of the iceberg, and this is how the logic behind that we're going to see next. So let's just start with a formal definition and the problem setting of classifying data, categorical data with decision trees. We've got a set of possible instances named X uppercase, because this is in fact a set. So this set contains all possible ordered tuples of discrete values. This means that each tuple is a possible combination of those ordered tuples, and these are every instance part of this set is called a feature. We've got Y, which is the target value that we want to predict, and we're doing classification, so this target value must be discrete. Then we want to find a function that allows us to map from X to Y. I mean, we want to find an approximation from this mapping. That's all we want to do. That's the problem. That's it. And we're going to define as well a set of function hypotheses, H. Each one is a possible candidate for reaching this target function that I've talked about. So our input will be this kind of thing, that this is a tuple. Notice please that xi is in bold, because this means that every xi is a vector, is a row vector, and yi is a value, is just an animal, is just a number, is a discrete value. So our input or training samples are a collection of this that we're going to see later. How does this look? So don't worry about it. And the output that we want to get is this hypothesis that best approximates this function. Again, if this sounds a little bit abstract, don't worry about it. We're going to see an example of this. Any questions? So further, we're going to see an example of this. So, for example, imagine that you have the task of predicting whether a tennis game was played given the following variables or features. The first one is the outlook. These variables is categorical, of course, because the possible values that it can take are sunny, overcast, rain, and that's 3 values. Temperature, which only can be hot, cool, or mid. Humidity, which only can be high or normal, and wind, which can be weak or strong. So based on these features, you want to predict whether the tennis game was played or not. So please notice that each column represents a feature, and each row of this matrix of this table is a labeled instance. This could be named as labeled instance or a data point as well for short. I will do it interchangeably. I will say labeled instance, data point, but it's meaning the same. Okay. So when the class labeled denotes whether the tennis game was played. That's it. So X, remember this definition. X is the set of all possible combinations of these variables of outlook, temperature, humidity, and wind. So X, we know how many elements X has. We know that X could have 36 elements because that's combinations of all possible data points that we've got. And we want to know Y, which is the set containing just 2 discrete values, 0 for no and 1 for yes. So we want a function that, again, maps any element or any instance of X to Y. That's it. And we want to approximate that function. This concept of approximating functions is quite powerful, and you will see it in all artificial intelligence. Almost any machine learning algorithm is just a function approximators, but there's lots and lots of different ways in which we can do that. So okay, so here start the exercise. I want you to, well, before going to the exercise, I want you to define graphically how does a decision tree look like. So this is a tree. We're already familiar with trees. So the root, or better, each internal node, like this, or like this, each internal node represents a feature or a variable. For example, each internal node here of Luke is a feature, humidity is a feature, and wind is another feature. So each internal node is a feature. That's it. And each feature or each internal node could have branches. So the branch of an internal node are all its possible values. We've seen that outlook can have sunny, overcast, or rain as possible values because they're categorical. Remember, we're working with categorical data. Then we've got wind and we've got humidity. So please notice that the branches of this internal node are just its possible values. So and each leaf node is a prediction. So yes, in machine learning, we'll talk about accuracy and we'll talk about metrics because the answers that we can get are not always right. And we want to minimize the number of wrong predictions that we've got. So that scenario that Stian pointed out could be perfectly fine, could be perfectly plausible with this tree. But this tree could have a performance that could be better or worse. However, our task is to build the best tree possible. Well, not the best tree possible because that's a quite complicated problem. But in fact, the building a perfectly accurate decision tree with the least number of nodes or the least number of height is a NP hard problem. That's quite interesting. So that could happen, Sebastian.
Okay.
Yes. Please speak. Diego, cuéntame. English or Spanish? So now I want you to tell me which is the prediction for the following features. If we've got the outlook is sunny, the temperature is hot, the humidity is high, and the wind is weak, which prediction will the tree give us?
No.
No, exactly. That's correct. Let's hear one. So, firstly, our current node is the root, of course. So we ask ourselves, is this current node a leaf or decision node? The answer is no. So we go from this path. So we've got to pay attention to what is the value of our instance, this instance, and with which branch correspond to, in this case, is sunny. So sunny, we follow that path. So we go with sunny. And sunny leads us to humidity. Well, sorry for this typo, is not outlook, is humidity, so ignore this, please. So we are here in humidity. So again, we ask ourselves, is this current node a leaf or decision node? The answer is no. So we search for what is the value of our instance that corresponds to which branch. So in this case, is high. So we follow the high branch. And finally, the current node that we've got is a leaf node. And it's a leaf node, so we predict no. It was clear? Does anyone have a question? Or clear? Please. Okay, so now we're going to see this concept of decision boundary. And I want you to take a look at these pictures. Take a look at these pictures and tell me which characteristic of each one is interesting to you. So the concept of decision boundary is critical for any classification algorithm. And it can be seen as the space operation that the algorithm learns to make in order to classify data points. So, for example, in this binary classification problem, where we've got two possible target values, yes or no, notice that the decision boundary divides the space, the feature vector space, into two sets. The first set is all the images of the function that we're learning, for which the predicted value will be yes. For example, red could be yes, and blue could be no. So pay attention, these are different algorithms, k-nearest neighbor or just a regression. However, we are interested in knowing what is the difference in this decision tree and random forest, because random forest is a more powerful version of a decision tree. So what do you notice here different from the others? What pattern can you observe from this decision boundary? Okay, I know what you're trying to say. You're saying that effectively, notice that the decision boundary is like we're making either vertical or horizontal lines through the data. And that's it because we are making decisions with categorical data. So a categorical data is represented by a response. And each response divides the feature of vector space into a set or the other. So effectively, that's it. For example, this decision boundary is quite interesting. You've seen that depending, well, and the red color means 0 and the blue color means 1. And this is the decision boundary for this tree. So decision tree, allows us to construct this kind of surfaces that divides the space. Notice that each possible data point in this space is part of the X set that we were talking about earlier. So notice that all of the points are that fall here are going to be predicted with the class 0, and all of the data points that fall here are going to be classified with class 1. So notice that when we're dealing with lots of features, multiple features, for example here we've got 4 features, then the decision boundary will be a hyper surface, because it's going to be in a 4th-dimensional vector space. So this is quite important regardless of the algorithm, of the classification algorithm. There will be always a decision tree. And remember that at the beginning of this presentation, I told you that decision trees can approximate nonlinear functions. Why? Because, for example, in this case, a logistic regression learns a linear decision boundary to separate this function, this data set. However, there are data sets that are more complex. For example, this one, because you cannot draw a diagonal line in which that perfectly fits the data. Well, that will not be possible always, but we can do better, and that's the reason why there always exist different algorithms for different data. So we are interested in knowing the distribution of the data in order to know which algorithm we're going to use. Okay. So notice that, for example, if we've got 2 classes, this one and this one, and they are distributed like this, these data points can be easily classified with a linear decision boundary. However, these same classes cannot, because they are more intrinsic with each other. So we need to approximate functions that are non-linear, because the world is chaotic and there's always exists data that cannot be so easily separated or classified. Okay, so cool. But now let's see the point of the iceberg that I told you earlier, sorry. So firstly, I want you to imagine, let's do a little probability exercise. Are you with me? Do you want to do it? So I want you to imagine that you've got a coin, and it's a fair coin. A fair coin means that you've got 50% probability that you're going to obtain one outcome, and 50% probability that you're going to obtain the other outcome. There are only 2 possible outcomes. The possible outcomes are heads or tails. Yeah. So I want you to imagine, can you make a certain prediction of what will be the outcome if I toss a coin with this settings? Can we predict with certain confidence which will going to be the outcome?
No.
No, exactly, because it's quite complicated. And this simple experiment, this simple mental experiment, allows us to know about uncertainty. Uncertainty is the key for constructing a decision tree. So the answer is no, because the uncertainty in this scenario is maximum, because all the possible outcomes have the exact same probability of occur. So this is called a maximum uncertainty event. And this measure of uncertainty is called entropy. This is where entropy comes in. So entropy, you've maybe heard of entropy. Well, what have you heard about entropy? For example, tell me in physics, or what do you think that entropy is before making this mental experiment? There exist metrics that allows us to measure the level of uncertainty. For example, entropy and G index. These 2 are the ones that are used in order to build a tree, and we're going to see next how. So this concept of entropy comes from a field called information retrieval, which is a specific field of computer science that deals with the problem of how information is processed, the amount of randomness that a information can be processed with. So we can define the uncertainty as the amount of randomness in the information that we're processing. So this is called entropy or Gini index. And now let's see the graph of this metrics. So in this event, both Gini index and entropy are maximum. Why? Because if we plot the probability, if we've got in the x-axis the probability that, for example, label one could be heads, for example. In the case that they are equally probable, so heads is we've got 50% probability of we're going to obtain heads and 50% probability that we're going to obtain tails. Then that's where entropy and Gini index are maximum. So what does this have? Why are we studying this concept? Well, that's because we can contextualize these problems, or well, not these problems, but these measures in our context. So entropy can be seen as the level of impurity. Remember, I don't know if you've noticed, but in machine learning, we've got lots and lots of names for different things, and that's because, as we saw in the last class, machine learning is a conjunction of various fields. So, for example, statisticians call this entropy or uncertainty measure. The people from computer science that are in the field of information processing called entropy, etc. So that's why there's lots and lots of ways to referring to the same thing. So in our case, we're going to call this impurity. So impurity is the level of a group of samples that, or maybe the level of certainty that we've got in a group of samples. So I want you to look at these groups and tell me which group is more impure. Which group is more impure? This one or this one? Remember, we've got two possible outcomes or two possible values to predict. 0 is the green, is the red one, and 1 or yes is the green one. So I want you to tell me which group is more impure. Think about it for a moment. And yes.
Sería el grupo 1, ya que es el que tiene más variedad de datos en él.
Exactly. We're going to make the process to get there. So if we calculate, I want you to see each of these possible dots as a possible outcome. So we've got two possible outcomes, the green one and the red one. So there are only two possible outcomes. In the first group, we can calculate the probability of getting the first or the one, or getting a yes, simply as the number of occurrences divided by the total number of data points in this group. So the probability of obtaining 1 is 57% roughly, yeah? And the probability in this group 1 of getting the class 0, or the red dots, is just 42, yeah, roughly 42, because it's 3/7. So if we go back to this plot, you can see that the entropy is a little bit here. The entropy and the Gini indexes are a little bit here. So there's more entropy, which means that we've got a more level of uncertainty. Yeah. And then we've got the second group in which there are 8 data points, and all of them are of class yes or green. So in this case, the probability of obtaining a green in this class, in this group, the second group, is just 1. So the answer, the question that in the group 1, you will be more prone to error when you're trying to decide whether a random data point in this group would be green or red. On the other hand, in the second group, you can completely certainly predict that any data point in this group will be of class 1 because you've got 1 probability. You are completely certain. So here, the entropy is 0, and here the entropy is high. Next, we're going to see how to calculate entropy. We're going to see a practical example of that. So any questions until now? Everything clear? Everything's clear. Crystal clear?
Yes.
Perfect. Remember, if you got a question, don't doubt it and go ahead and do it. There's no problem. So next, these are the formulas for Gini index and entropy. They look a little bit overwhelming, I know. However, there's no big deal with this because for the curious minds out there, the way that this entropy comes from, remember that this entropy comes from the computer science and information processing field. This comes by measuring bits, the possible states of bits, and well, it's quite interesting. So I let you this link if you want to go deeper and know where these formulas comes from. So notice here that the notation tells us that PCI, P as a function of CI, is a probability or percentage of class CI in a node. And notice as well that for any node, we've got the branches of a node are its possible outcomes. So this is the sum of the probability of getting each possible outcome in that node. Okay. However, that's a good question because when we are comparing and we are deciding which node or which variable tells us more about the answer, we're going to make a weighted average between the entropy or Gini. Well, in the practical example, I will use entropy because that's how I learned it. However, it's not so important. You can use Gini. And if you're going to calculate this by hand, well, Gini is a little bit more practical. So they are almost, as you can see, they are measuring the same. So, but in a different scale. So, and in real world, there's no much difference. It's just by because this formula is a little bit more simpler. However, I wanted to use this formula because it's quite interesting how this comes from. So, for example, the logarithm base 2 here comes from the bits scenario that I told you about. For example, this coin toss can be seen as a bit, a single bit. It can have either 1 or 0. So we can calculate the entropy of different scenarios with these formulas for entropy and G. Okay. So now we're going to take a look at another important concept called information gain. Remember, the entropy or impurity or the Gini index are a kind of measurement of what is the level of randomness in the data that we're dealing with. And we don't want randomness because if we've got for example, if we've got a random classifier, you will get 50% probability or 50% accuracy if you repeat it infinitely by the law of large numbers, for example. And we want to get as much accurate as possible. So keep that in mind. And we're going to talk about information gain. Information gain can be seen as minimizing the entropy or the uncertainty by transforming the data, or particularly by performing separations to the data, we can minimize the entropy. We can get as well, if you remember from calculus, you can get in a complex function, you can get a global minimum, which is quite good in our case because we want to get the best possible decision tree. But as well, we can get a local minimum point. So that is well possible. So then, yes, information gain can be easily seen as just minimizing the entropy or reducing the entropy. Now, how can we reduce the entropy? That's a good question. How would you reduce the entropy? Well, we're going to see it next. If anyone has any idea, you can tell it, of course.
Quitando los datos atípicos del dataset.
Okay, yes. That's a way, however, that's not proper of the decision tree. That's more like a pre-processing step. Okay, so when you pre-processing the data before training it with a decision tree classifier, you are supposed to remove the outliers. Datos atípicos en inglés es outliers. Para que sigan porque hay tanta terminología. Bueno, datos atípicos en inglés es outliers. So yes, that's a way of getting a better performance, and that's why pre-processing stage data is quite important, and is typically the process of this stage that we spend more time in. So it's quite important. That's a good question. Well, that's a good point. Next, now we're going to see the practical example, or well, the theoretical example, and then we're going to show you how to implement this with a pseudocode. However, you're going to see that it's a little bit simpler when you get the idea. So, firstly, we have to choose the root, and then you're going to see that the process, you can repeat this process recursively. Remember that we're dealing with decision trees, so recursion is quite normal in this kind of problems. So imagine that you are assigned the problem or the task of predicting which drug is better for which person, because some persons, for some people, there will be better certain kind of drug, and for other people, there will be better other kind of drug. In this case, we've got two possible drugs, drug A and drug B. So these, well, anyone tell me, please, how is the name of this variable and what is the name of this variable? What is the name of this variable and what is the name of what is the variable? What is the name, sorry, of these variables that I'm pointing out here? Remember, we want to predict this variable in function of these variables. And all of them are categorical. This variable doesn't really care about this variable because this has no meaning in the problem. So this tells us nothing about how to get from here to here. Well, anyone, please, if anyone wants to talk, just do it. I'm just returning to my question. The answer is that this variable is the target variable, is the variable that we want to classify, is the objective variable, is the target variable, is the dependent variable. So notice that there exists lots of names. For example, mathematicians call this variable dependent variable and these variables independent variables, because remember that when we've got a plot, the x-axis the x-axis is independent, and we've got the value for the y-axis based on the x-axis. So the y-axis depend on the x-axis. The same is the same idea here. So, well, the difference is that we're now dealing with high dimensional data. That's quite normal in machine learning because we've got lots of variables to deal with. So this drug variable is called, again, the target variable, the interested variable that we want to predict, there's lots and lots of numbers of names, sorry. And these variables here, these four variables here, they are just the independent variable, or the predictors, or the explicative variables, or the features. I would call it features because it's shorter, so I prefer that. And each row here is called a data point or an instance. A data point could be labeled, and we say that a data point is labeled when we've got both all the independent variables and the target variable. And we've got an unlabeled data point if we've got the independent variable, but we don't have the target variable. So for example, this last row here is a unlabeled data point because it's got no label. This is also called label. So that's the terminology. That's basic terminology, and we'll be using it for the rest of the explanation. So now we're going to see each feature, and we're going to know which tells us more about the objective variable that we've got. Yes, anyone? Gonzalo, Sebastián?
No, tener la mano levantada.
Me estabas preguntando cuál sería la predicción, ¿cierto? Aquí.
No, bueno, pues por ahora no lo podemos responder porque no tenemos el árbol, pero vamos a ver.
Ah, ok.
Vamos a construir el árbol ahorita sí. Vamos a ver qué es. Es sencillo y hay que hacer varios cálculos, pero esos cálculos pues los hace el computador. Pero miren la importancia.
Si yo veo que todos los middle age son droga B, ¿es suficiente razón?
Vamos a ver que tiene mucho que ver. Tiene mucho que ver.
Okay.
Es una muy buena observación. So let's continue. So yeah, we want to know which attribute is best. And it's like we were filtering out which values. Imagine that we've got kind of a system that filters the data. For example, we've got here 14 observations, I think. Yeah, 14 observations. And we've got here all of those 14 observations. So each red circle represents a drug A, and each green triangle representing drug B. So we're going to partition data based on the category of each feature. So let's start with cholesterol, and what we're going to do is calculating the entropy with each partition. So for example, for cholesterol, we're going to have two partitions because cholesterol has two possible values. So now let's see how it is done. We've got these values and these values, and we've got three, for example, with the people with high cholesterol, if we filter the data, but all the people that just have high cholesterol, and we take a look at what is the value of the target function for the data points that are that apply with this criteria, i.e., we taking the people whose cholesterol is high, and we ask each of them which drug was predicted, or which drug was recommended for the doctor. So we've got here three of the people that have got high cholesterol were predicted with the drug A, and 5 with drug B, and for the people with normal cholesterol, 2 of them were predicted with drug A, and 4 of them were recommended drug B. That's clear, isn't it? Yes. I hope that yes. So let's see the same with sex. Let's see. Please take a look at these groups, at these petitions. Take a look at this. And take a look at this. If we repeat the same process with sex, take a look at this group and take a look at this group. Now the question is, before going any further, the question is which group, which feature is less impure? Remember, this is sex and this is cholesterol.
El menos impuro sería el sexo, ¿no?
Exactly, yes. Because just it's quite graphical. Because we've got, for example, the probability of obtaining a drug B, given that the sex of a person in this data set is female, is just the number of green dots divided by the total. So in this case, we've got 2, 4, 6, 8. So it will be 7 divided by 8, which is quite high. And the probability of that a person will be recommended with drug A, given that the sex is female, is just 1/8. And that's it. It's clear, isn't it? It's a simple idea that we can repeat, and we can get results quite amazing. This is amazing, guys. So take a look at how simple ideas can have a good performance and can be quite beneficial. So now, if we were going to calculate this probability again, before going any further, we want to know which is the entropy of all the data first. Before doing any partition, we want to know which is the entropy of all the data, and that's simply counting the number of positive classes and the number of negative classes. Well, in this case, counting the probability of obtaining a drug A and drug B. And this is the starting entropy. Remember information gain. We have to measure the entropy before making a split and after making a split. So again, I'm using here the entropy formula. However, you can do whatever method you want. You can use the Gini index or the entropy formula. Now, the entropy formula here is the probability of obtaining B, which is 9/14. 14 because it's the total number of data points, and 9 because there are 9 persons, 9 people for which drug B were recommended. And we multiply it by the logarithm base 2 of that value, and we subtract the probability of obtaining A and multiply with the logarithm base 2 of the probability of obtaining B, which is 5/14, because there are 5 people for which drug A was recommended. There are 14 in total. Is it clear? This looks a little bit messy, but it's quite simple. Just a lot of calculations that a computer can do. Is it clear? Okay. Remember, this is the formula. This is the formula, and this is just a sum. That's it. Now we're going to say we already have this starting entropy value, and we want to minimize this. So we're going to filter the data. It's like filtering out the data here. Remember, it's like filtering the data based on the criteria. So here initially we've got an entropy of, well, quite high entropy. That's normal. For example, if we've got a data set for which the half of the data were of one class, and the other part of the data is from the other class, the starting entropy will be 1, because there's lots of uncertainty. So that's a good observation. And if we filter the data by cholesterol, and we repeat the exact same process. So notice that the difference here is that in order to calculate the entropy of partitioning the data by normal cholesterol is just taking into account only the data points that have normal cholesterol. So we count with respect to these, with these yellow data points. And we do the same for the high the people with high cholesterol. Is it clear? For example, with normal cholesterol, we've got 6 people for which drug B was recommended, and 2 people for which drug A was recommended. We repeat the same process, and we've got this value, and we do the same for high cholesterol. We've got the same value, and look, take a look at this. The entropy is 1 because we've got the same number of positive and negative classes of drug B and drug A. So here there's a lot of uncertainty, and here is a little bit less uncertainty. Now let's do the same exact process for sex. So now the sex tells us this. So we repeat the same process here. So we filter the data for the people with a female, the data point with female value for the attribute sex, for the feature sex. We count again the same. We've got that with female, we've got three of them were recommended drug B, and 4 of them were recommended drug A. And we've got this value of entropy, and we do the same for male, and we've got this value of entropy. Is it clear until now? Any question? Now, the question is, which partition give us higher information gain after doing the split? Remember, it's like we're filtering data. It's like we're filtering out data on computing the entropy for each possible outcome of each categorical variable. And the question is, which one is the exact same process for the other ones?
Okay.
It's just because if we repeat the same thing, well, it's just kind of boring. So, but I hope that the logic is clear. Again, you can use the same logic, exact same logic for blood pressure and for age.
Y lo ideal sería hacer eso, ¿no?
Yes, exactly. Yes.
Okay.
¿Y uno hay que comparar las medias o qué?
What?
Uno o sea, para comparar las entropías, pues uno compara la media de las entropías de una variable con la media de las entropías de la otra.
That's a good idea. It's a good idea, but what is the problem with the idea? The problem is that in that case, computing that average would give the same importance of each possible value. But we want to know which feature gives us more information about the data. So we can do better. We can do a weighted average. And the weight of each term in the average would be just the frequency of that outcome in the data. Let's see now. So yes, how do we calculate the information gain?
¿Dice que vas a hacer una media ponderada?
Yes. Yes.
Okay.
So how do we calculate the information gain? Well, it's fairly straightforward. Remember that we've started with this entropy, and we want to compare which split give us more information, or which split after which split we have less entropy in average. You know, given a weighted average. So the weighted average for knowing or for assigning each of them a value of entropy, well, it's just going to be weighted by this. This is, remember, this is the entropy of splitting with all the patients with female sex. And we're going to, the criteria for making the average, or for making the weighted average, is the number of observations. So notice here that in the sex, when female, to the females in this data, we've got 7 females, and in total we've got 14 females. So we take into consideration the number of instances in the data, and that will be kind of a score of how many importance are we going to give to the entropy of that partition. Because think about it in this way. It will be not so good to give much importance to a feature that is quite unlikely to happen, but that isn't quite that hasn't appeared frequently in the data. So that's why we give this kind of a score for making the weighted average of this whole entropy. So this term here is the total entropy, is weighted and average entropy of this partition. And the same here. This value here is the weighted average for the entropy of this partition. And this value is nothing more than the starting entropy that we found earlier. It's here. So we just subtract them, and we pick the root. We will pick as root the feature that give us more information, the feature with which we gain more information. All right. So in this example, sex give us more information because the entropy, well, the information that we've gained is this amount. And if we make separation or we filter the data by cholesterol, the information that we've gained is less, is this value. So if this value is greater than this value, then we're going to pick sex as our root. And that's it. Is it clear? ¿Hello?
Sí.
Es que al principio estabas midiendo cuál, la idea del principio era medir cuál de los dos tenía una menor entropía, y ahora estás midiendo cuál de los dos tiene más información, ¿no?
Exacto, sí. Porque, otra vez, la entropía y la información son como contrarios. Entre más entropía, menos valiosa es la información, porque hay mayor aleatoriedad en la información, hay más incertidumbre. Entonces, nosotros queremos tener un clasificador que sea lo más seguro posible. Entonces, nosotros queremos reducir la incertidumbre.
La entropía, el máximo valor que puede tomar es 1. Sí.
Sí. Yes. So that's it, guys. It's quite simple. Now the rest of the process is repeating these for all the features. ¿Cómo?
Hurtado ahorita de decir algo.
Ah, sí, cuéntame.
Que la entropía esa del 0,940 ¿de cuál es?
Esa es la entropía de todo el dataset sin filtrar nada, porque nosotros queremos ver qué tanto mejoramos conforme vamos partiendo los datos. Entonces, mira, en total tenemos 14 filas, ¿no? 14 data points. Entonces, nosotros tenemos al principio 9 de todos estos son drogas B y 5 son drogas A. Entonces, la entropía inicial simplemente pues calculamos las probabilidades. Mira, aquí está como lo calculamos. Ajá, esta. Mira que es 5. Bueno, primero es la probabilidad del primer evento, o mejor dicho, la probabilidad de la primera clase que queremos predecir, que simplemente es 9 sobre 14, 9 porque es la probabilidad de obtener aleatoriamente, o sea, es como si aleatoriamente, sin hacerle nada a los datos, y te taparas los ojos y escogieras a una persona de todas estas. Entonces vos vas a tener 9 catorceavos de probabilidad de obtener una persona a la que se le diagnosticó, a la que se le recomendó la droga B, y lo mismo con A. ¿Sí ves?
Listo, entiendo.
Vale, bien. Entonces, so that's it.
Si se hace con Gini Index.
Gini Index is the same. It's the same process. It's just a function that changes. The Gini Index formula is this one. And remember, it's just this probability squared and 1 minus the sum of all the probabilities for each class squared. It's just that. So in this case, for example, this case would be 1 minus 9 over 14 squared plus, well, 1 minus and big parentheses there, and 9/14 squared plus 5/14 squared. And that will be the index, the Gini index for this, with this partition, with no partition.
Yo digo es el gain information.
It's the same. Now, instead of computing the entropy for this node and this node, you would use just the Gini index. So, for example, the Gini index here, in a normal clusteral scenario, would be just 1 minus big parentheses 6/8 plus 2/8. And that will be the Gini index. It's just a value that changes. It's the same idea, but with different formula.
Y la idea es hacer esos cálculos para todas las variables, ¿no?
Yes. Initially, we want to do this calculation for all of the independent variables. So here, I just made it with sex and cholesterol. Later, you will do it with blood pressure and H, and all the entropy, the weighted average entropy, all the well. You will choose as root node the partition or the variable that gives you the highest information gain. And that's it. So in this scenario, we will choose the sex feature because that's the one that gives us the more information gain, the highest information gain out of these two. Now you can repeat this process with H and with blood pressure, and you pick the one that gives you the highest information gain, and that will be the root. And then the process is quite the same. Just what is the difference? That, for example, we choose sex as our root node, and there is a stop criteria. When you have a node for which entropy is 0 or which Gini index is 0, that will be a leaf node. And that's new. And the logic behind it is that you keep repeating this process over and over for each node until eventually you will get a leaf node which will have a entropy of 0 or a Gini index of 0. Yes?
¿Cómo determinas que una variable no tiene ningún tipo de relación? O sea, a la que no valdría la pena hacerle nada de eso.
Well, making these calculations. For example, if the information gain for a variable is zero, then we will just know that that variable doesn't contribute at all to predict the objective function. For example, that could be a case. For example, imagine that you're programming this, you're quite happy programming this, and you forget to drop this variable, patient ID. And then you compute the entropy for this variable that, of course, doesn't tell you anything about the objective variable. It doesn't tell you anything. It has no relation. And the entropy for this variable will be almost 1. Because if you take a look at this, if we use this variable, what will be the entropy? It's not 1. I tell you, it's not 1, but it's close to 1. What will be the entropy if you choose this variable?
Eso no sería 0, la información que nos da.
Yes, will be 0. Yes. And why
¿Me preguntaste?
0?
¿Por qué? Porque pues es un ID. No tiene nada que ver la droga que se le da a un paciente con su ID.
Yes. And take a look at this.
Porque son todos los valores diferentes.
Ajá.
No, eso ya.
Pero además, piden que si escogemos esto, tendríamos 14 ramas, ¿cierto? Y la probabilidad en cada una de ellas, la probabilidad de obtener una de estas va a ser o 0 o 1. Pero cuando hagamos el weighted average, eso nos da exactamente esto. un valor muy parecido o sea, la entropía va a ser altísima. Entonces esto no nos da ninguna información, ¿ok? Y así ustedes se dan cuenta qué variable aporta más o menos a predecir lo que queremos predecir. And that's it. And now the process continues. Now, the difference is that at the beginning, we had into account all of the data. However, remember that we are filtering out data. So, for example, if we want to make this rotation, we will take into account all of these data points. Not these ones. No, this ones, no. These data points. And we will repeat the same process with all the variables, except the one that we've chosen with, i.e., we will take in this internal node, we will choose this internal node, taking into account the age, the blood pressure, and cholesterol. And that's it. Sex not because it won't have any importance. So that's it. So basically, you repeat this process recursively until you've reached a node which entropy is 0. And you will stop there, and you will label that node as a leaf node or decision node. And then you will, or either, that's one case, or either another case is that you can define a maximum depth of the tree. And that is useful when you don't want to overfit the data. Because if the tree gets too deep, then you will probably overfitting the data. You will probably be building a decision tree that fits perfectly the data that you've trained it with, but that's not the case because that tree wouldn't be able to generalize well. So you can limit the max depth of the tree to prevent overfitting. And this is the pseudocode for the decision tree algorithm. As you can see, you're saying all training instances to the root of the tree, set the current node to the root. Well, you can read it, it's quite clear. So that's it. Any questions until that? Well, we are almost over. That's quite simple, you know. Well, basically, I promised you that I will show you a pseudocode. Well, this is the pseudocode and a semi-implementation of this. So this could be an implementation. You could have this. You could have this attribute. That's it. So yeah, you can construct, of course, these diagrams as well. It tells you a lot about the data, and that's, well, these are the resources that you can take into account. So that's it, guys. Well, no se alcanzó el tiempo para hacer esta partición, pero se la tengo de tarea. Y eso es. ¿Profe, vas a decir algo?